Comparative study of SEPIC converter commands fitted with classic MPPT algorithms combined with 2 cascaded pi correctors. Abstract: instantaneous extraction of the maximum power available at a photovoltaic generator, GPV, terminal and its transfer to the load requires some techniques. The most practical is the use of an adaptation stage between GPV and load. This paper presents a use case of a single-ended primary inductor converter, SEPIC, as an adaptation stage in a PV system. The converter performance is evaluated by applying 2 different most used maximum power point tracker, MPPT, methods, including the Perturb and Observe, PNO, technique and the conductance increment. Several works investigate in this field regarding these commands. However, this work shows the efficiency of algorithms PNO as well as conductance increments cascaded with 2 proportional integral, pi, controllers. These allow regulating and stabilize voltage output and the current in the system while keeping the reference from the MPPT. The goal is to extract the maximum power whatever the sunshine variation, the temperature, and the load. Keywords: MPPT control, SEPIC, pi controllers, PV system, GPV, PNO. Introduction. Using photovoltaic solar power is the most elegant way to produce electricity, without moving parts, gas emissions, or noise. It consists of converting abundant and non-exhaustible sunlight into useful electrical energy. Photovoltaic, PV, systems generate power dependent on climate conditions, such as solar radiation, panel temperature, and the change of the charge. Hence, an extraction technique of the maximum power point, MPP, which control the direct current to direct current, DC/DC, converter duty cycle is required to ensure suitable operation of the PV chain in different operating conditions. 7. Prior works investigate the problem of finding operating point which allows extracting the maximum energy from PV modules using SEPIC converters controlled by MPPT regulators. Some Paper 124 proposes algorithms which use a very popular method based on the value of the reference voltage instead of MPPT algorithm output. Other uses MPPT but combine it directly with pulse width modulation, PWM, technique 12. The objective of this work is to improve the energy efficiency of the standalone PV system using a SEPIC converter. It is controlled by a conventional PNO MPPT as well as a conductance increment, where output is used as a reference for the pi voltage regulator. This paper organized as follows: in Section 2, we will see the whole system to study. Section 3 presents the modeling of a PV module. Section 4 is devoted to the operating principle of SEPIC. Section V discusses the pi controllers. In Section 6, we talk about the classic MPPT command. In Section 7 and 8, the simulation and interpretations of the results, and finally the conclusion. System presentation. The system contains 3 blocks including a PV generator, an adaptive stage and a set of batteries. The adaptive stage is controlled by MPPT to ensure the continuation of the optimum operating point. The batteries store energy produced by the PV module during the day, phase sunshine, and stored energy is used during the night, dark phase, or when the solar radiation is insufficient. Synoptic diagram of a standalone PV system. Model of a PV module. Modeling PV cell behavior uses the solar radiation properties and those of semiconductors. Multiple mathematical models of a photovoltaic cell exist in the literature. 1.5. The goal is to generate the current voltage characteristic, IV, in order to analyze and evaluate the photovoltaic module's performance. The single diode model is the most classic and the most commonly used model, due to its simplicity and precision. 11. From a behavioral point of view, Figure 2 shows an equivalent model of the ideal cell including a diode in parallel with a current generator, where M is the material index, between 1 and 2 depending on the technology, K, the Boltzmann constant, T, the temperature in Kelvin, Q, the charge of the electron. For a given temperature and irradiation, the photocurrent IPH and saturation current ISAT are defined in equation 2 and 3, where EPREF, current at reference temperature, SS, temperature coefficient given in the datasheet, GREF, reference irradiation, 1000 W/m2, e.g., width of the prohibited band, is a TREF, saturation current at TREF. Figures 3 and 4 show the characteristics IV and PV obtained under the influence of the change in temperature, for a given G, and sunshine, for constant T. Modeling a SEPIC converter. The main role of the SEPIC converter is to form an impedance adaptation. In that case, the GPV delivers the maximum power irrespective of the value of the load. Synchronous converters, SEPIC or CUK, are now becoming more advantageous than other converters due to the reduced current ripple and better efficiency. It is used for interfacing the PV generator output to the load as well as keeping the maximum power point 11. Fig. 5. SEPIC converter. Analyzing its operation will be done in two phases according to the conduction state of the switch K. A. Energy accumulation phase. When switch K is closed, the converter behavior is described by the equation 4. B. Recovery phase. When switch K is open, the equation 5 describe the converter behavior. The state model of the converter is deduced from equations 4 and 5 during a TC switching period. This model is presented in the equation 6. The corresponding Simulink simulation model is shown in the figure 6. SEPIC simulation model. Pi regulator. The task of the regulators is, firstly, to compare a reference value with the corresponding measured value. Secondly, it acts on the control quantity to make the measured value as close as possible to the reference value. A voltage regulator. The voltage control loop regulates the generator voltage PV around the constant reference value delivered by the MPPT algorithm. It also controls the process of loading and unloading of capacitors C1 and C2, according to the load variations 9. Equation 7 describes the transfer function of pi tension regulators. Where is the own pulsation and is the damping factor? NW. B. Current regulator. Another pi regulator is useful to adjust the current of the inductor L1. It corrects the error between measured current IL1 through the inductor and the reference provided by the control loop of the PV generator voltage. MPPT command. The MPPT control is essential for an optimal operation of a photovoltaic system. The principle of this control is based on the automatic change of the duty cycle to an optimal value in order to maximize the power output of the PV panel 1. A. The Piano algorithm. The Piano algorithm is widely used because of its simple structure particularity with the fewest measurement parameters. To use it, we consider that the PV generator works at a point which is not necessarily the ppm. The principle of the Piano command consists of triggering a disturbance the GPV voltage and observing the power variation 5. B. Conductance increment. This method focuses directly to the power variations according to the voltage. The conductance is the quotient of the intensity of the voltage. The incremental conductance is the quotient of the variation between two time values of intensity by those of the voltage. Comparing the conductance with the incremental conductance, Fig equals. Simulation setup. The entire system is formed by a PV generator including 12 panels connected in series, a SEPIC converter and a resistive load. The control part has 4 Simulink blocks. The first function block contains the classic MPPT method which uses Piano or increment of conductance. 2 blocks of pi correctors control and stabilize the output voltage and current according to their reference. The last block contains the control law of the SEPIC converter. Results analysis. Figure 13, B, shows that with the 2 MPPT controls, the curves of the optimal voltage and the corresponding maximum power merge. We can notice the immediate recover after a sudden change of irradiation, response time t equals 0.06 s. However, the zooms in figure 13, C, shows that with Piano, there are a voltage ripple and a lower power value. The figure 14 shows the system behavior with the variation in temperature of the panels. We will observe that with these two commands, the system is stable only after T equals 0.04 s of sudden change in temperature. Its power gets back and always follows the maximum power value whatever the change. Figure 15. Conclusion. In this paper, the models of a PV generator and a SEPIC converter have been presented. We have seen two different techniques for optimizing the power supplied by the GPV. Note that the value of Pmax, with these two methods, oscillate around the value of the MPP. It means that these methods can be used to determine the MPP. The results confirm the performance improvement of the conductance increment. Indeed, with the latter, the response time is faster and error steady state is low. Contrariwise, with PNO, we note the existence of a small voltage ripple. Obtained results also shows that the system adapts well to external disturbances change, temperature and sunlight. Its efficiency consists not only for tracking maximum power point but also the response time and stability.